The topic of this talk is inverse analysis of driven pile capacity in sands. It was originally intended to be presented at the University of Tennessee at Chattanooga's Research Dialogues in 2020. That conference was canceled due to the COVID-19 virus. So I'm presenting it in this way. The STADYN computer program, which is this is one of a series of talks starting with dissertation and with one presentation at the IFCEE in 2018. The STADYN computer program was developed to analyze both static and dynamic installation response of impact pile driving systems. When we have an impact pile driving system, we have to consider both the static response of it. We think of a static load test, but ultimately we have to think about what load we're actually putting on the foundation, and the dynamic installation response, which includes what happens while the pile is being driven, and specifically in this case for impact pile driving. This program has been worked on for the last 5 or 6 years. Recent developments, we've broadened the application of the program to piles driven to primarily cohesionless stratigraphies. The original study was mostly with predominantly cohesive stratigraphies, but now we're branching out into cohesionless stratigraphies. Previous applications of the program to an inverse analysis used a test case from the New Orleans area, and it had many problems, not the least of which was there was no static load test to go with it. There were other problems with the pile, and you can look at some of my earlier work on the subject. What we really needed was a well-documented test case to compare with STADYN, one which had both static loading, dynamic loading, and the data that came out of that. And the data in detail. Many times the length of limitations of much of the published literature really doesn't permit presentation of all the data. In this case, we used an FHWA study. The FHWA study we used was the replacement of the Route 351 bridge in Hampton, Virginia. And the test case featured plastic piles of 2 different kinds, but ultimately they wanted to compare it with a 20-inch pre-stressed concrete pile. And we're going to focus in this particular presentation on those 20-inch pre-stressed concrete piles, the test program for that. It is well documented in the document you see, extremely well documented in fact, and that was one of the things that made it attractive to use. You can see the pile configuration. The pile was fully instrumented from top to bottom, although in this study we concentrated principally on what was going on at the pile head. And the pile is 18 meters long, and it is 610 millimeters square, or 20 inches, and it has a standard stress strands and all that. So there's nothing really extraordinary about this pile other than the fact that it is so fully instrumented. The stratigraphy is a mixture of silty sands and some clays. And what we had to do to start with, we wanted to do this in the forward method. So what we did is we took the data that you see on the left and converted to the data you see on the right. And the data on the right is in what the program's own Xi-Ada data, soil data configuration. What that means is this, is that the soil itself can try to reduce using standard values of soil properties, and I know that there's some limitations with that. We'll come back to that. The Xi represents the degree of cohesion of the soil. In other words, a -1 specifies a purely cohesionless soil, a clean sand or something like that. On the other end, a +1 represents a soil which is actually purely cohesive, like clay, very fine clay, with everything else in the middle. The eta represents the soil strength, with -1 being a very loose or a very soft soil, and a +1 being a very dense soil. So we had the pile was had force on top of it in a number of ways. One way, of course, in the upper right-hand corner is the static load test, which is obviously done after it's installed. We also had PIT testing in the lower right-hand corner of the slide, and this became very important, as you'll see in just a minute. On the left side, those are the three, as in the case with the static load, we see the FRP composite pile and the plastic composite pile. But this study is going to concentrate on the pre-stressed concrete pile, and we see the pile head response to that, both the force and the velocity times impedance response to it. We have also had data on the axial load strain behavior and Young's modulus of concrete, which are obviously two related, and that's where we ran into our first difficulty. Those last charts indicated that the Young's modulus was around 22 to 25 GPa, which some of you who are familiar with this particular type of concrete pile know that that's probably on the low side. And that became evident in a hurry when we put that data into STADYN. There was very poor phase tracking between STADYN. Basically, the way the STADYN is done backwards from CAPWAP. In STADYN, we start with a force time, and we measure the velocity time at the pile head that comes back, and then compare it with the original. When we did that, what happened was that we had phase issues, we had other issues, we had some magnitude issues, and this suggested that the material properties that were given were not applicable to what we were actually doing during pile driving. The results from both the PDA and the PIT suggested that if we assume the concrete is a standard density, then the Young's modulus is around 39.5 GPa. And standard values of piling indicate more around 32.7. And we're going to use both of these. STADYN's is drawn from kind of typical values, and that's always dangerous, particularly with concrete. For materials other than steel, one of the things we found is that it's very important to make sure that you've actually matched the properties of the pile to the one you're using during analysis. And we'll actually look at both of these. We have 5 test cases. Oh, by the way, before I get into the test cases, if you look on the right, there's another pile driving summary given in the report where the wave speed is about 3,800 meters per second. And actually, both of the other cases indicate, and you can read the paper for more details, in excess of 4,000 meters per second. That is another discrepancy. One of the things that learned from this study is that if you're using existing data, it pays to make sure that data is internally consistent. And the whole concept of the scientific method is that we can replicate things either physically, or if we're trying to develop simulation techniques in simulation. And it's very important to make sure that the properties you're using are actually what the material actually has. There are 5 test cases. Test cases 1 and 3 use the low value of Young's modulus. And, this would be kind of simulating if you're using the program in sort of a naive way and you're trying to just throw it at a project and see what will happen. This is frequently the case. In many cases, when we run wave equation analyses, we don't necessarily have the data for the specific concrete or in wood pile have the same problem. Wood in question. So we have to use standard values. Cases 2, 4, and 5 use the higher Young's modulus and the higher wave speed. And case 2 is the forward method, and cases 4 and 5 are the inverse method. The difference between 4 and 5 is that the 4, we try to reduce the number of layers and thus the number of variables that the program is optimized, at least the soil variables, by trying to reduce the layers of what the soil borings indicate that we should have. In case 5, we simply say that, well, we're just going to play ignorant and basically say that we don't know, and then we will use the way that we divide the pile up. In STADYN, generally divide the pile up into meter-long segments, and we'll just get soil data for each one of those segments and let the chips fall where they may, so to speak, and that's pretty much what we see in CAPWAP studies. And you can see visually the difference between the reduced stratigraphy based on the actual stratigraphy, and then the full discretization on the right. The layering becomes very obvious, the significant difference between the two. You'll also notice that STADYN models the pile as hollow, which it, for point of fact, wasn't, as you saw in the earlier slides. The reason for that is this. STADYN is an axisymmetric model, and therefore, in order to make it so that the pile will have the same wetted surface as the square pile does, and the same cross-section the square pile does, we end up with a hollow pile. So that's why you see that. That's not an ideal situation, but the situation is a limitation of any axisymmetric models. And axisymmetric models are fairly common with in the finite element analyses. We're starting to see that getting away from that, but for the moment, this is what we've got. All right, let's look at the forest time histories. And we're looking at the last 3 cases. These are all the inverse cases. And you can see that for case 3, you can see the phase shift issue coming up just a little bit. It's not as dramatic as it was when we in some of the original cases when we were using the much lower values of Young's modulus, but you can see some of the phase shifting there. Case 4 is with the reduced layering, and case 5 is with the full layering. And you can see that those are better than, they're not much different from each other, but there's some different from each other. In fact, in terms of the static low capacity of file, they're dramatically different from each other, as we'll see in just a minute. But the results are better. One thing that was a little disconcerting to see was the fact that the computed pile head Z times V was lower than that of the much lower than the actual. In the initial impact, it was better on rebound though. Static load test results. Actually, the original static load test was a little above 3,000 kilonewtons for the Davison load. You will see that the cases 3 and 4 are closer to that than case 5. Case 5 is interesting. It's the full layering. It is almost identical to the CAPWAP result. It is also the only case where we saw plunging failure within to achieve Davison criteria. The original static load test, as you may remember, actually did that. But with case 5, we have we have a straight drop off, whereas with the other two, it's more of a gradual, and that's something that characterizes the static load response in STADYN from the very beginning. Virtually all the cases have a more gradual drop off. The case 5 is is not necessarily the first time, but is one of the first times, particularly with actual data, where we see that. And it's the only place is the only case that actually replicates that part of the actual results. The optimization tracks are in case 4 on the left, the reduced layering, and case 5, the full layering on the left and the right. And you can see that this is a very unusual. You're starting to see these tracks more in the literature and they're basically the optimizations which we used a polytope method with annealing. And this is standard with STADYN. We see that as it goes along and searches to the different cases, and eventually it settles out to one specific case. It should cut off sooner, but there's some chatter in the data, and it doesn't really do that very well. But it's still better to run it too long than not long enough. So you see that by about 1,500 optimization steps, the reduced layering is done. It takes about 2,000 to get to the for the full optimization. We obviously that's a result we expect, because the more variables you have with this, the longer it should take to actually filter through those and come out with a result. The black line at the very bottom of both of them is actually the RMS difference between the actual velocity and the computed velocity, which is how we signal match in STADYN. A summary of the results show that the second case, where we actually did a forward method, we put those xi and eta variables that we estimated and came out with that result. It's actually closer to the static load test than the other ones. That, of course, brings up a good question of, well, then why isn't that the best case? It depends entirely upon the setup factor. That was, in the original study, the CAPWAP result, which is virtually identical to our case 5 in terms of Davison load, was set up, had a very large apparent setup factor. And just looking at the stratigraphy, one would, in my opinion, not think that that'd be the case, but it very well could be. And it turned out to be the closest match to the CAPWAP, which attributed that to setup. The blow count variance, I think one of the STADYN's weaknesses is it doesn't really have a good way of estimating blow counts. For STADYN to do that, we have to go on a lot longer runs than it does now. And in fact, the runs in this particular case were limited by the data. We could only signal match for the data that we had. The maximum tensile stresses, the case 1 was the closest to the original, and the maximum compressive stress was a little above actually what the original would say. The RMS norm, as you see with the case 3, which was using these typical values, we got an improvement when we went to case 4. We got another improvement in that case 5, but look at the variance in the Davison load between cases 4 and 5. That little table at the bottom gives you a weighted xi and a weighted a. In the case of in the 3 cases where we used the measured or estimated Young's modulus. Note that in the case of the xi, the values in the inverse methods were positive, tended to be positive, not much, but some. But in the case of the forward method of our own estimate, tended to be negative. This stratigraphy looked more cohesive to the pile than it did to the than the borings would indicate, which indicates that piling that the xi eta, which is strictly set up based on typical values and typical, we may need to make some adjustments in terms of the way we do forward methods with that. Eta, actually, the inverse methods show that the results were indicated a softer soil or a looser soil than we had with the forward method indicate, than just looking at the soil data would indicate that we had. And that, of course, was borne out to some extent with the results we got with the Davison mode. Conclusion, again, the difficulties with the Young's modulus determination highlight the importance of critically analyzing published data in the course of each use. If we're going to do this, we need to be able to back check it and make sure that it's internally consistent and makes sense. The inverse methods indicated a more cohesive stratigraphy than examination of the boring summary would indicate. This may mean that how cohesive a soil is for driven pile analysis may vary from what is typically shown in the unified system. Going from the reduced layering to the full layering analysis produced different results. We did this in the original study for this using a cohesive stratigraphy. The results were inconsistent with the full layering. In this particular case, they were a little better, but it's still difficult to tell. In any event, I thank you very much for your attention. If you want more details, you can read the monograph, which is both on my website, vulcanhammer.net, and also is at researchgate.net. Thank you.